All right, welcome back, and today we're going to talk about network reconnaissance. And this is a very big topic, a very important topic, because it refers to identifying whatever is currently running in your network. From a hardware perspective, what nodes you have connected to the network, what servers, what endpoint devices you have, what networking devices you might have, down to the actual software and the services that are running on those pieces of hardware. And this is, again, it's very important because it applies to security from two different and opposing perspectives. First of all, from the good guy perspective. When you're performing a security assessment, the first thing you need to determine is what's currently running in your network in order to later determine where your weaknesses might lie and what you might need to improve. So that's the very basic first step of any security assessment, performing a network reconnaissance. Secondly, the second perspective, from a bad guy perspective, that's the attacker's point of view. That's because the network reconnaissance operation or process is actually the first step in an attack as well. You know, the attacker has to discover what's currently in your network in order to determine what's the weakest link or what are the actual low-hanging fruits that it might exploit. So we should know what reconnaissance tools we have at our disposal for both an audit assessment perspective and also to better understand on how we should react when we find ourselves the victims of a reconnaissance phase that might announce a much nastier attack. And reconnaissance can actually lead us to monitor even more than just hardware and software. Since most attacks are being conducted over the network, well, monitoring network traffic is also an important part of a network assessment and also can be performed using network reconnaissance tools. So looking at hardware, software, and network traffic. All right, so let's start with the basics. And when I say basics, I'm actually referring to the basic ipconfig command or ifconfig command. Now, who hasn't used ipconfig at least once? Simple enough commands, but they are the basics of other tools as well that deal with topology discovery. That is, determining how the actual network looks like, how it is structured, how many subnets does it have, how many hosts are there connected to each network, what's the exit point, what are the default gateways from each and every subnet in there. So we can start with these basic commands. On a Windows host, ipconfig provides basic information such as the current IP address assigned to all the interfaces actually of your host. Also the subnet mask in order to help you determine what is the network that the host belongs to, and also the default gateway. That's the exit point from your network whenever your host needs to connect to some other destination that is not inside of its local network, the internet here included as well. Now, we can also enrich this command with the /all flag at the very end, which is going to provide you a lot more information, especially the MAC address or the layer 2 information for your network interfaces. And by the way, this is also one way of figuring out if the IP addresses and the configuration has been learned from a DHCP server, so has been automatically assigned by a DHCP server inside of your network. DHCP stands for Dynamic Host Configuration Protocol. It's a very well-known and well-used protocol in most local networks that help us whenever you plug your network cable or connect to a wireless network. Helps you quickly get all the information that you need in order to communicate inside of that network and even outside of it. Things such as your IP address, the subnet mask, the default gateway, the DNS servers that you can use, and a lot more optional information if needed. By the way, notice that ipconfig also provides you with IPv6 configuration information if it is currently enabled on that specific network link. On Linux, things kind of look the same, except that it's ifconfig and stands for interface configuration, not ipconfig, and it kind of mashes all the information here in one single output. A little more difficult to read. You can see we have IP address information in the INET field right here. We have the net mask, we have the broadcast address. We also get the IPv6 network assignments, and also the Ether field standing for Ethernet. This is going to be the MAC address of your current network interfaces. By the way, network interfaces in Linux, they're going to be often named as ETH followed by a number, or ENS if it's running inside of a virtual machine. And it also provides you with a bit more information here regarding the number of packets that are currently flowing through that network, like how many packets have been seen, sent or received over that network interface, and how much traffic in bytes has been recorded through that interface. This is also sometimes a good way to troubleshoot connection errors, just to see if the packets are flowing. You might have a defective link, packets might be flowing only in one way. This is one good way of checking out if something is not working right. And also you have some statistics here regarding the errors, like CRC errors, checksum errors on your frames, errors due to misconfiguration, bad cabling, maybe errors generated by too many packets trying to enter the network interfaces at the same time and filling its buffers. Now, the ifconfig command is unofficially a bit starting to be deprecated in Linux distributions. What we're currently using nowadays is the IP command. You can type it as IP address or IP address show, or the way I like to do it in a shorthand notation is IPAS. And not only it provides you with a nicer looking, colorful output here, but also the output is just a bit different. You can see it highlights the important stuff in here, like the Ethernet address, your IP address, network mask in here, broadcast address, right? And also the IPv6 addresses that you might have assigned to your interface. All right, so that's how we get IP information related to the current host. Let's go one step further and try interrogating outside hosts, other hosts on our network or outside of it. And we're going to start here with ping. I mean, everybody has tried ping before, I'm sure of that. Ping is just an implementation, a command line implementation of a certain combination of ICMP message codes. ICMP stands for Internet Control Message Protocol. It's basically a protocol developed a long time ago to help provide some sort of a metadata or connection status information along with the other internet protocols out there. So it's basically some sort of a management reporting protocol in a very, let's say, simplistic implementation because it's very old. But nowadays we can use specific messages in ICMP, specifically echo request and echo reply, and that's the exact implementation of the ping command. You're sending an echo request if the host or the network interface is programmed to listen to such requests using the ICMP protocol, responds with an echo reply, and you get the result that looks something along these lines right here. You're basically being told that you are receiving a reply. Notice that by default on Windows, you only get 4 requests and 4 replies, also denoted here at the bottom. And the size of the message that is being sent, how much time it took for this message to come back. So that's the round trip time of your communication, and also the time to live here. That's the IP field time to live, which is a field set in IP packets that is decremented by 1 on each layer 3 network hop, like router or a firewall. And nowadays we use this field to determine the distance in network hops between the source and the destination. Traditionally, it was used to avoid routing loops, to avoid having a packet loop infinitely all over the internet. On Linux, the output is somewhat similar, except for the fact that by default, the ping command is going to run indefinitely. So it's not going to stop here. You can break this execution here with Control-C, but you can also set the number of packets to be sent using the -C parameter. So 1, 2, 3, 4, and 5. And we stopped, and we also received the same summary statistics just like in Windows. Now, how many we sent, how many we received, how much packet loss we had, 0 in this case because we did receive an answer for each and every one of them. And what's the total time, all the average time taken for these replies to come back to us. Now, another use case for ping that you've probably seen before is also to check whether the DNS resolution works. I mean, there are better tools out there, of course, but simply by pinging something like Google is going to not only solve google.com into the actual IP address of Google, and by the way, notice that I'm currently resolving the IP address of Google into an IPv6 address. All right, so this is going to be a ping over IPv6, but it also tells us that we have connectivity to google.com. Now, one thing to keep in mind regarding the ping commands, I've seen a lot of people, especially students that are just learning about networking and security, considering that if a ping command works, everything else should work. And they're sometimes surprised to see that they have something like a web server. They ping the web server replies, but when they enter the web server's address, the same very IP address that they used with the ping command in a browser to actually receive the contents from that web server, it's not working. And that's simply because the ping command is, just like we said before, it's an implementation of the ICMP protocol. Basically, if we are able to ping a destination on a network or on the internet, it only means that we have ICMP connectivity to that destination, not any other type of connectivity, not on any other protocol, not on any other port. So don't forget about this. Don't be fooled by the fact that if the host replies, any type of traffic is going to work. In most cases, ICMP might work, but actual web traffic might be filtered. In other cases, you're going to see that web traffic is going to work, but ICMP is blocked because it's considered to be a risky protocol that can be used for network reconnaissance, just like what we're doing right here. So don't forget about this. ICMP is just a simple application, just a simple protocol. If it works, it only proves that ICMP works, not all the other applications that might be running on the same destination. Nevertheless, one of the things that you can use ICMP successfully for, or the ping command successfully for, is to check for network reachability. That is just validating whether you actually have valid routes and your routing is working in order for you to reach that destination. I mean, if the ICMP packets can reach that destination, it's pretty sure, there might be some exceptions in there, it's pretty sure that any kind of traffic can reach that destination as well. If there are any other firewalls or any other security rules that might be dropping that traffic, well, that's a completely different story. Another simple tool is the ARP command. ARP, again, is a protocol in itself, and it stands for the Address Resolution Protocol. What does it mean exactly? Well, it's a protocol that we're using whenever a host needs to send some traffic on a local network. So we have the data nicely packaged, we add a TCP or UDP header on top of it, then we add an IP header on top of it, and then we need to add a MAC layer on top of it. So we need to know the IP address of the destination that we're talking to, and most likely we are going to know the IP address because we know where we want to send that packet, right? But we're also going to need to build the layer 2 packet as well. So we need a layer 2 source address, which is going to be our own MAC address on our own local network interface. And we'll also need a layer 2 destination MAC address. Well, now depending on where that destination is actually located, if it's inside of our own network, then it's going to be the actual MAC address of the destination host. If it's outside of our local network, then it's going to be the MAC address of our default gateway, of our exit point from our local network. So one way or another, we need to figure out what is the MAC address, the layer 2 address of either the host that we intend to communicate with or of the default gateway. And we have a protocol that deals exactly with this situation. That's the ARP protocol. The ARP protocol has a very simplistic implementation. It simply sends a broadcast. That's a message that reaches everyone in the local network asking, hey, is there anyone with the IP address 192.168.0.1 in my network? If you do have this IP address, please reply to me. Right? Everybody receives that message. Those who do not have that IP address simply ignore it. But the default gateway, for example, that might have that IP address responds with a unicast message back to the source saying, well, I own that IP address. Here's my MAC address. If you want to communicate with me, please use this MAC address as your destination. So that's the ARP protocol. And of course, all this information has to be stored locally on our hosts because the hosts actually are the ones that generate the network traffic and build the packets. And we can also see the cache being generated by this ARP protocol using the command ARP. On Windows, it's going to be ARP-A. And you can see here that we have a separate table for each interface on our system. So we have one interface that's 10.100.101, right? That's one network interface. It's connected to a separate network segment, and these are the MAC addresses that they have found out about from that network segment. Notice that for the second interface, for example, we have dynamic and static entries. Now, the static entries here, most of them deal with broadcast addresses and multicast addresses, and we're going to talk about these later on, but the dynamic addresses are the ones that are actually being learned from the ARP protocol using the exact method that we described before. So in pretty much any situation, hosts inside of a network are going to have at least a dynamic entry for the default gateway because they're probably attempted to communicate with the outside world at least once during their lifetime since they booted up. On Linux, we have pretty much the same command. It's ARP, not APR, all right? And we have, again, entries and mappings between IP addresses and layer 2 addresses right here. Hardware type means Ethernet, the interface that this mapping is associated to, and also the flags right here. Flags of C means a complete entry. This again is a dynamic entry. Static entries are going to be marked with an M or permanent entries. And of course, you can statically add your own as well. On Linux, for most commands, of course, you probably know this, you have access to the man pages that are going to tell you all the flags and switches that you can use for each command and explain some use cases and even provide some examples for them. Now, this ARP table is actually a very important weakness in network security. That's because the very implementation of the ARP protocol is completely insecure. And I'm not just talking about the fact that the communication is in clear text, but there's no way of validating the source of the information that a host receives whenever they send an API request. And also, unfortunately, a host doesn't even need to send an API request to get a reply and to learn from that reply. There's something known as a gratuitous ARP reply, which is basically a way of saying that at any moment in time, I can send an ARP reply to a host that hasn't even requested one and provide that host with whatever information I want to provide it with. For example, I could tell that host, you know what, the default gateway is not where you thought it was. It's now actually located at this MAC address right here. And guess what? Perhaps that MAC address actually belongs to my own machine, an attacker's machine, inside of the same network as my victim. And this is one way of performing something called ARP poisoning. So injecting fake information into ARP tables, which leads then to a man-in-the-middle attack. Simply because if I manage to trick a host into sending me the traffic that is normally destined for other hosts or for the default gateway, I can intercept that traffic and inspect it and find out confidential information or steal data from it, for example. But that's discussion for another video. And let's not forget about routing. Routing tables are everywhere, not just on routers, because routing, the decision itself, has to be performed based on some sort of a routing table. Now, for most hosts, mainly, we're going to have a very simple routing table. That is, we have a route that tells the host, well, if the destination is in the local network, then you should be using this interface to communicate directly with it. And if the destination is not in the local network, then you should send your packets to the default gateway and then leave the default gateway to handle that traffic. We don't know where the destination actually is. It might be on another network. It might be all over the internet. It might be on the other side of the world. We don't know exactly, but we know that we should send to the default gateway all the traffic that we don't know how to get to. Now, as I said, we have routing tables on hosts as well. On Windows, with the route print command, so we can see the active routes right here. We have an IPv4 route table and, of course, separate an IPv6 routing table because they're two completely different protocols. And for the IPv4 one, for example, we have the network destinations on the left, the net masks, because we need to understand which type of destinations fall into all these ranges here on the left. Gateway, just in case we are using a gateway, a default gateway, for example, to get outside for the internet connections, right? So this network destination of 0000, also known as a quad 0, with a net mask of quad 0 as well, is basically a way of saying that any destination that there's no entry in the rest of the table for is going to be reachable through this gateway right here. This is the router on our network. We know this is the only exit point from our network. If the destination is not local, is not on link, then it should be somewhere outside. Right? If it's not in our house, it's probably outside of our house. And this is also the network interfaces that we're using to go outside. We also have metrics. Now, not going to talk about metrics so much here, just to remember that the metrics is a numerical identifier that helps us prioritize certain routes over others. Very relevant when we have multiple routes for the same destination. Like, for example, when you have multiple internet service providers, multiple internet connections. Now, on Linux, of course, things look pretty much the same. We can start with the route command. It's the kernel IP routing table. Again, it's only going to show us the default route here, okay, with the default gateway. Again, the destination of default here is actually an alias for the quad 0 that we saw before. You can see the mask is quad 0 as well. And also we get the local route right here. Local route here basically tells us that whatever falls within the range of 192.168.100/24, that's the mask right here, doesn't need a gateway because we're directly connected through the network interfaces ETH0. Now, since we are now starting to use the IP toolset, we also have the IPRS, stands for IP route show command, which is going to provide us pretty much the same information as before. Finally, we have the traceroute utilities. Now, they're not actually that different. We have traceroute, traceRT. They're just different commands for different operating systems out there, but they pretty much do the same thing. Now, their implementation slightly differs, but they all have one thing in common, and that is they're trying to determine not just if the destination is answering, like the ping command, but what are all the network hops along the way to reach that destination. So if we are directly connected with the destination, we're in the same network, well, traceroute is pretty much going to work just like ping. But if we are trying to reach a destination from the internet or from some other network out there, we might be interested to see, well, what are the network nodes through which our packets have to pass through in order to reach that destination, and also how long do those packets actually take in order to reach that destination. On Windows, for example, we get the traceRT command. And if we were to address a destination on the internet, such as google.com, we can see that on every network hop in here, the utility is actually trying to resolve that IP address that is hitting into a valid DNS name, providing us with more information as to where that node is actually located. And you can see that after 9 nodes or so, we have actually reached the end destination for google.com. We can also see the delays, how much it took for each node to reply. Now, the traceRT utility on Windows actually relies on ICMP packets as well. Remember that TTL that we talked about, that time to live inside IP packets? Well, we can actually play with that field and send packets with a TTL of 1. And that's going to cause the packet to be decremented, to have its TTL decremented at the first hop. And when that TTL goes down to 0, there's a special ICMP message called ICMP time exceeded. That's one way of notifying the source of that traffic that your traffic has quote unquote expired. So we're not going to be able to forward it to its end destination because its TTL expired. So that's one way of figuring out where exactly that TTL went down to 0. Now, if we think about traceroute, we can actually imagine that this first message right here was sent with a TTL of 1, which made my local router reply with a time exceeded. Then we send it with a TTL of 2, which made the next router after my home router to reply with a time exceeded, and with a TTL of 3, which reached another ISP internal router, and then TTL 4, which went even further, and so on and so forth. And apparently with TTL number 9, we actually reached the end destination. So we're actually waiting for those time exceeded messages to be sent back to us in order to understand where and what type of node did that time exceed operation actually happen. And this is how traceroute actually builds your output right here. On Linux, we have traceroute. So it's not traceRT, we have traceroute Microsoft.com in our example. And you can see that the first items right here are pretty much the same because I'm using the same ISP as before, but it's also a bit faster. And that's because the traceroute implementation on Linux actually uses UDP probes instead of ICMP. So it's not waiting for a time exceeded message, and ICMP probes are sometimes slower and sometimes they're ignored altogether. Well, the traceroute implementation on Linux actually uses UDP probes, which are not only faster, but sometimes are even more reliable. One more tool that's worth mentioning is the path ping tool. You can see the line right here. It's path ping followed by a destination. You can see the first thing it does is performing kind of like a trace route, and that's going to take a while. You can see here computing statistics for 225 seconds. It's actually going to attempt to generate statistics for latency and packet loss for each and every node along the way. Here's the result right here. So that's path ping for you. Now that's an equivalent for Linux of what you just saw, and that is MTR. My traceroute or something like that. Now, in most Linux distributions, you might find it available, or you might need to install it from the default repositories. In my distribution here, which is a Kali Linux, the version that gets installed is a graphical user interface one. So if I were to enter in here, let's say Amazon.com, press enter, we're going to see that we start getting all of these statistics regarding packet loss, delay, how many packets were sent, what's the best round trip time, what's the worst round trip time for each and every node along the way until the final destination. So remember MTR on Linux for the pretty much the same type of statistical information as path ping. And by the way, these types of statistics are not just useful from an administrative point of view, like determining which node along the way is performing the worst, maybe where's the actual delay happening, if the users are complaining. But also, a unexpected delay, a huge delay on a single node along the way might also indicate a potential security incident happening in there, like a router that is under a denial of service attack. So that's why we're looking for this type of information in a security training as well. And finally, we get to talk about Nmap. Now, Nmap is a very popular free open source utility. It's a command line utility by default. It also has a graphical user interface implementation called Nmap, and it's somewhat the Swiss Army knife of network discovery. And it can do a number of stuff related to network discovery, starting with the actual discovery of the active hosts on your network. Now, you could probably do this using the ping command as well. So you could do something like this, just iterate from 1 through 255 and execute a ping command with a count of 1 on all the IP addresses starting with 192.168.15. Whatever the counter is, the one from 1 through 255. Well, you get this result here, you pipe it, you send the result here to the find command, and then you match only the lines that include a reply keyword. Let's see how this works. Now, I'm going to wait some time here while it's cycling through all the possible IP addresses in our network, and you can see that we get some replies in here. Those are the hosts that are up in our network. Now, it does take some time. It doesn't provide you with that much information except for the fact that they're actually answering for ICMP requests, but you could probably do some sort of a host discovery process using ping just like that. So after a couple of seconds, this is the result. These are the hosts that are answering to ICMP echo requests. So one of the simplest first type of scans you can perform using Nmap is by just looking at which hosts are up in your network. You can enable this using the SN flag at the very beginning. This is the equivalent of a ping sweep, which doesn't scan any further than actually determining whether the host is up or down. Now, as you can see, the results come in much faster. You're going to receive all the IP addresses that have responded to Nmap requests, and you also get a couple of information here regarding their host names just to figure out which one is which. That's simple enough, but the default behavior of Nmap, so if you just enable Nmap followed by the subnet or the IP address that you intend to scan, the default behavior is going to be to first perform that type of network discovery and then perform service discovery. So this scanning type is going to take just a bit longer because if a host replies as being up, then Nmap is going to elevate its scanning attempts and try to determine what type of applications, what type of services are actually running on that host. Right, so we got the results in here after a couple more seconds, and let's see if we can determine some interesting stuff. So starting with the first host that was detected from the first ping sweep as well. This is my router, right? You can see it has a couple of services open on it, running on port 80 for the web interface, also on port 443 for the HTTPS version. I have the printing protocol. We also have some domain name services enabled on it because I'm using it as a DNS server. Let's move forward here. This one here is a smart home device from Sensible, dealing with air conditioning. An IP camera right here, accessible over port 80. Probably not a good thing. And also the big one right here, the one that has a bunch of open services, running services open here. This one is a NAS, a network attached storage device running in my home. You can see I'm using it for a lot of stuff in here, running a lot of services. They're all going to show up here with their port numbers and their corresponding protocols. All right, you can scroll down here and find more devices running on your network. Of course, not all of them are going to be so open, and you're not going to always determine all the services. So you can see that we actually scanned 256 IP addresses with 2 hosts up. We found 12 active hosts on our network, and this scanning took 55 seconds. Now, Nmap is actually a lot more evolved than this, and you can use it with a couple more switches in here. And you can find all the possible switches in the man page for Nmap. That's the command of man Nmap. And if you scroll down here to the help section, you're going to find that we have a number of methods of performing host discovery. Right, the one that we've just used was SN. This is a ping scan. Actually, it's a way of scanning that disables port scan, which means I'm just determining where the host is up. I'm not going to move forward and scan the ports on that host as well. Now, the interesting ones are down here under scan techniques, and these are the techniques that we can use to discover the services that are running on the host. The first one here, the capital S scan, the TCP SYN scan. This is also called a half-open connection scan. Remember the TCP three-way handshake, where we first send a SYN packet and wait for a SYN ACK back before we send our own acknowledgement back to the destination? Well, this one right here attempts to send a SYN packet and waits to see whether a SYN ACK comes back, but it never fully closes the connection. It is considered to be, or at least the capital S here, stands for SYN as well as stealthy. Well, it's not so stealthy anymore, at least not nowadays, but in the old days with the old firewalls, you had the chance of not being detected if you did not fully complete a TCP connection. So that connection would never be logged, and your scanning attempt would never be detected. Now, it's not the case anymore, but the scanning technique still remains right here. The other one here, the capital T, this one is the connect method. This one actually performs the full three-way handshake. And this is the least stealthy method, of course. This one is the most visible one in all the logs, in the web server logs, in the firewall logs. Everybody's going to see that you're actually attempting to scan those services. You can also perform an ACK scan, where you're pretending that your packet belongs to an existing connection and you're initiating the connection already with an acknowledgement packet. Again, some firewalls may be fooled by this, others might not be. We also have UDP scanning techniques. And we can also combine a lot of the options and the flags in the TCP packets by setting specific flags. You can even set all the flags in a TCP segment, and this one is called a Christmas scan. Kind of like, setting all the flags lights the packet up like a Christmas tree. Or you can simply customize which flags you want to enable. A zombie host, the SI right here, also called an idle scan. This one is a very smart type of scanning, where you're actually relaying your scanning packets through another victim, through another zombie host, so-called. Now, it doesn't have to be a compromised host. We're simply looking at the incrementing sequence numbers that are being generated by that host in order to determine whether our replies, our relayed replies, have received an answer or not. And another very useful section right here is the port specification and scan order. We have the -p parameter, which specifies the exact port ranges that you want to scan. You can either specify a single port, once or multiple times, or you can specify an entire range of ports that you need to scan, or even a specific list of known ports. Now, we can even go further and start asking more information about a single host. So, for example, remember that .99 host that I had in my network. This one was a network attached storage device. We could either use the -O flag here at the front in order to perform OS fingerprinting, that is determining even what type of operating system it's running on that device, or we can even combine all the scanning techniques into one single one with the capital A switch. This one performs as well OS fingerprinting and service discovery and version discovery, and throws everything it has at this host right here. Of course, this is going to be a very intrusive type of scanning. It's going to be detected by all the IPSs, IDSs in your network, so careful when, where, and to whom you're doing this type of scan. All right, scanning complete. After a couple of seconds here, we're going to receive a report that tells us what information Nmap was able to glean from all those open ports. Starting with, for example, port 80 right here, you can see that the service behind it is an Nginx Linux server, and tells us the HTTP title here is "Hello, welcome to Synology Web Station," which immediately tells us that this is a Synology device. How nice is this? You can see it also has some ports open for Windows file sharing, another instance of Nginx, this time listening on port 443 for HTTPS, for secure connections. You can also get some information about the SSL certificates that are available right here. And incidentally, in the subject alternative name, we can also see the name that actually leads to this device through its certificate. Finally, moving forward here at the bottom, there's going to be a service information. This one right here attempts to identify the operating system that is running on the host. Now, in our case, it doesn't know exactly what type of operating system is because it's something non-standard anyway, but it is some sort of Linux. and it is based on a Linux kernel 4.4. So this is, again, very useful information for a security audit from an inventory perspective, but also from the perspective of an attacker, because if you're able to reach devices like these from the outside network, from the internet, well, attackers will be able to reach them as well, and they'll be able to determine the same information as you just did. Now, Nmap comes with a predefined database which can be updated from time to time of the platforms that it is aware of, as in all the hardware platforms or the operating systems out there. And this database is called the Common Platform and Enumerations database. And this one right here is one such entry. This is one way of saying in one single line, in one single string, what type of device is this? All right, so coming back to our slide right here, we've seen that we can use the Nmap for network sweeps for discovering all the active hosts in a network. We can use it to further drill down and figure out what services are running on those hosts, what versions they are, what actual implementations they're using, and also identifying the operating system behind that host. Now, this is not going to be a 100% valid information every single time. There's a lot of assumptions being made in here, and Nmap tries to look at a lot of indirect information that is going to lead it to determine that it might be a Windows server, it might be a Linux server with a certain percentage of certainty, but it's never going to be 100%. Another very simple tool that's available on both Windows and Linux is NetStat, network status basically. It's a simple tool that lists all the active listening ports, open ports, and active connections on your machine. It's a great way, if you have enough time and resources to process all that information, to determine whether there are malicious services, foreign services that you might not know nothing about, running on your hosts, which might indicate that there are some indications of compromise in there, that those hosts have been compromised. Here's an example NetStat output on Windows. You can find the status of the connection, what is the local address and local port, and the destination address and the destination port of my connection. You can see connections constantly being created on the HTTP and HTTPS ports of remote web servers. Some of them hosted on EC2, probably on Amazon. So these are websites that I currently have open in my browser that are periodically refreshing things like, Gmail and the calendar and all the resources behind those pages. And by the way, on the left-hand side here, if you see some services that are listening right now on ports that you know nothing about, that might be a potential indicator of compromise. Now, that's a huge number of network reconnaissance tools out there. Just to mention a couple of more right here, we have the Harvester, which is an open source intelligence gathering tool, which is going to scan things like Google and social networks and LinkedIn for valid email addresses, no domains, subdomains in a specific company. So it's a way to gather publicly accessible information, which provides you some more insight as to what are the valid email addresses or how that company is actually organized internally. Another tool that most people don't really consider to be a network discovery tool is curl, C-U-R-L. That's a simple command line tool, in most cases used to craft web requests. Now, most people don't know this, but the CURL tool can actually talk over a number of protocols out there. It can talk over email protocols. It can talk to FTP servers. It can even talk to Windows file shares. So we can use this to craft specific requests to get more information about the status of a server. For example, its banner information, its login information, perhaps even in an attempt to generate some responses from an email server in order to determine whether a certain email address is valid or not. Nessus is, again, a very well-known tool, commercially available tool for performing vulnerability scanning. Now, of course, we're going to scan for vulnerabilities only after we've built a thorough image or map of our network. So we've scanned our hosts, we scanned what hosts are up, what services they're running, what versions they're running, and then we're going to look for certain vulnerabilities that match those versions. Finally, Scanless is a tool that attempts to evade intrusion detection systems that are going to fire up an alarm whenever they see scanning traffic. Scanning traffic is easy to detect, right? It's a bunch of requests coming in a short time span, sent towards a large number of IP addresses and even a large number of ports in sequence, perhaps. So Scanless attempts to use some relays or other sources on the internet to slowly send that scanning traffic so that it's going to evade detection. Now, this might sound like a tool for hackers or for someone who's planning an attack, but think about it the other way. If you're on the defensive side, you might try to use this tool to figure out if your security systems, if your IDSs detect this type of scanning traffic or not. So are you vulnerable to this approach or not? And we should never forget about DNS, because DNS is at least the public DNS, is a huge publicly available source of information about what is currently available and exposed and publicly accessible in your company. So we have some tools in here, some command line tools, starting with NSLOOKUP on Windows and Linux, dig and host, most likely Unix, Linux type of utilities that allow us to craft specific DNS requests in order to elicit some type of response from the DNS server itself. Now, there are situations where the DNS server can actually host accidentally more information that is useful for the outside public, in which case they're exposing some valuable information that can be extracted using these hosts. And in other cases, the DNS servers themselves store some additional records that indicate who is the admin for that specific zone, what type of security measures are in place, or even what type of third-party tools out there they're also using, which are some records that are most generally stored in TXT type of records in DNS servers. Now, gaining access to all that kind of information can be a goldmine sometimes. Here's some example of outputs using the aforementioned tools. So for example, with NSLOOKUP, Amazon.com, we are first told the DNS server that we're currently using. Of course, we can override this and query a specific DNS server out there, and then we get the answers that are actual IP addresses that point to Amazon.com. Same goes with host, with the host utility right here, or the dig utility. I've added a -T capital A flag in here just to be more explicit, in which case I wanted to select only the A capital A type of records out of this zone, which means all the IPv4 to name mappings. And again, we get the same three results right here, all of them being a capital A type of record. Now we can also query for different types of records. So for example, if I'm interested in what are the mail exchange servers at Amazon.com, what are the email servers basically, I can send a simple request like this, and I can see that the email for Amazon.com is handled by amazon.smtp.amazon.com. This is the actual server that is delivering mail sent to Amazon.com. And then I can craft a capital A type of record for this email server, and it's going to provide me with the resulting IP address. Now, a dangerous practice that sometimes creates a huge vulnerability due to misconfiguration or to configuration error is the ability to perform zone transfers from the outside world, from the public internet. Now, a zone transfer is a functionality in DNS servers that is used to synchronize multiple DNS servers internally. So it's a functionality that should not be accessible from the outside because it allows an attacker to simply dump the entire database that is stored on that DNS server. Now, there's a publicly accessible service out there that allows you to perform such a zone transfer for teaching purposes, right? And you can see the actual command for the dig utility is AXFR. That's zone transfer. All right. The first item right here, that's going to be the name server that we're currently using to perform that zone transfer. And the second argument is the actual zone that we're requesting. Now, hit enter, and you can see that you're going to receive a lot of information this time and a multitude of record types. Not just the capital A record, not just the name server, but even the records that point to internal private IP addresses, even records that include administrative information right here. So it's basically a way of dumping all the information, all the database inside of that DNS server. This is something that should not be open to the internet, but sometimes it is. Finally, there's DNS-enum as well, which helps you package in one single request a lot of tests and a lot of sub-requests that attempt to display or reveal how much information you're actually exposing to the outside world. Remember, these tools are not for you to become an attacker. These tools are for you to test your own systems, to test how your company, how your domains, how your network looks like from the outside. And if it can be queried this way, and how much information are you giving out for free. And there's one more thing that we can look out for, and that is analyzing network traffic in order to perform network and host discovery. Because by looking at the network traffic, you're going to see the actual traffic that is being generated by the hosts on the network. You're going to see the routing protocols, you're going to see the management protocols that are going back and forth over there. So there's a lot of information that you can analyze just by looking at the network traffic that will help you determine what's inside of that network, what's running in there. Now, capturing network traffic sounds good, but it's the toughest thing to do. There are a number of places where you can actually capture and decode this type of network traffic. The most obvious one is at the network interface itself on a host. And in order to do this, we have a number of utilities, such as the TCP dump utility and Wireshark, which you probably used before or heard about at least, and in a graphical user interface manner. Now, these utilities rely on the fact that the network card, the network interface, is able to present them with all the packets, even those that are not destined for that network interface card. It's going to be able to present them all in a nice output or package them in some sort of a packet capture file in order for that result to be further analyzed. So later on, you can look at whatever packets were captured and try to figure out, is there some unencrypted traffic going on in there? Are we communicating with illegitimate hosts that we don't want to communicate with, such as sources for malware or bad domains with bad reputation? So that all that information can be gleaned from that packet capture. So this is one way of capturing traffic, right, on the network interface. It's not going to be easy to perform this on each and every host in a network, of course. So a better solution would be to think about capturing traffic on a network segment, that is capturing all the traffic that is traversing a specific network segment. For example, the uplink connection from your company switch or a floor switch towards the internet router, or even from the internet router to the internet. Now, there are network devices out there, smart network devices, that have appeared on the market lately that have the ability to actually perform this type of packet capture by themselves. It's not an easy task. It requires a lot of CPU and memory resources and some disk space to store the resulting packet capture, especially if it's a core switch, which probably sees gigabits of traffic every single second. So capturing all that traffic, it's not going to be easy. It's not going to be efficient. But it is possible. It is possible that for specific links, you can configure a switch in a so-called span mode or a port mirroring mode, in which all the traffic on a certain port is being mirrored or created a copy of that traffic and sent on a different port. Now, on that different port, ideally you have some sort of powerful machine, a server that is able to capture all that traffic and then store it and analyze it further. So that's another way of doing it. And you can also do this using a passive device called a TAP, a test access port, which is basically just a T inside of a network cable, which basically acts like a mirror of a traffic on a network segment. It's not a switch in itself, it's simply a device that whatever comes in one port goes out the other, and also a copy of it is being generated on a third port where your network analysis device lies. Now, the simplest type of packet capture we can perform with TCP dump is to simply specify the capture interface. So I wanted to capture all the packets that are going through this interface, inbound or outbound. Of course, there are a lot of filters that we can add, so we can, get some more sense out of all this this output right here. For example, filter only for specific destinations or only for specific ports or protocols, right? Only the things that actually interest us. But each line right here in this output is basically one packet. You can see the timestamp, the protocol, who sent it, over what type of protocol or what source port, destination port. Of course, there's a lot more information available in the man page for TCP dump. And besides the count, the number of packets that we can capture or the output to a file, the most important parameter here is the capture expression, which acts as a filter for selecting which type of traffic are we interested in viewing. So if you scroll down here under expressions, you can see that the expression selects which packet will be dumped. If no expression, all the packets on the net will be dumped. All right. So some examples in here, you can see that we can filter only for traffic arriving or departing from a specific host, or we can even filter down to specific TCP flags, TCP ports right here. Or you can even filter based on the packet size. You can see here, this one here prints IP packets longer than 576 bytes sent through the gateway SNUP. Or we can print all the ICMP packets that are not echo requests and replies, so which are not ping packets. So the expression would be ICMP type not equals ICMP echo, and ICMP type not equals ICMP echo reply. Pretty obvious, right? Now, luckily, we also have Wireshark, which can present the same information in a much nicer graphical user interface, So we can see the protocols right here, the source, the destination, the timestamp, and some information about this packet right here. You can see them flowing around here. We're already 150 packets captured over the course of like 10 seconds or so. So there's a lot of information right here. Of course, we can even filter this all this display using a display filter right here at the top. And incidentally, the same expressions that we can use with TCP dump can be used with Wireshark as well. So if I'm only interested in, let's see, for example, ARP requests and replies, I can see only the ARP messages right here. Here's an address resolution protocol packet right here. I can see the Ethernet header. That's the destination, which is a broadcast, right? Because it's an ARP request. There's a source generated by one of my devices right here, and there's the actual payload of the ARP protocol right here. Now, the packet captured can be dumped into a file with a PCAP extension, and the format of the files is the same between Wireshark and TCP dump. So you can capture packets using TCP dump and then graphically analyze them using Wireshark if you wish. Finally, it's worth mentioning that a couple of reconnaissance techniques rely on injecting or crafting fake packets and sending them into your network just to see how the network reacts or how the security devices react. Well, of course, if you're on the defensive side, you should probably take care of analyzing how your network reacts to such crafted packets. Now, among the tools here listed are hping, which is not just a packet injection tool, not just a packet crafting tool, but can also perform network scanning, kind of like Nmap, and also can be used to generate flooding traffic like a denial of service attack. So it does a simple command line utility that you can actually test your services, your outside exposed services, to see how they behave if a denial of service attack happens to hit them. Another one is Scapy. That's a small Python utility that can be configured to generate any type of traffic you want. You want it to generate fake web request, it can do it. You want it to generate fake BGP updates, it can do it. So you're basically a small traffic generator or packet crafter that allows you to configure absolutely anything from the outside headers to the inner payload and then send that traffic on its merry way. TCP replay, as the name says, it's a tool that can capture traffic and then replay it back. Now, the replay attack was for some time, nowadays not so often, was a favorite method of bypassing authentication systems and security measures. That is, by simply capturing the authentication sequence between the user, a valid user, and an authentication server, and then replaying that same sequence back without even knowing that user's password, you're sometimes guaranteed entry through that authentication service. Now, of course, there are other situations out there where vulnerabilities to replayed traffic can be found, but this tool right here can help you identify if you are vulnerable to such type of attacks. And there's also one additional use case. If you have happened to capture some anomalous traffic, some traffic that you just guess that it might be part of an attack, you don't know exactly how, you could capture that entire traffic and then replay it back in a controlled environment through a number of security devices and scanning engines that might apply more or less complex traffic signatures in order to detect whether that traffic actually included or not an attack attempt. Finally, there's an interesting set of tools called exploitation frameworks. These are more complex systems that allow, especially attackers, to determine first the available vulnerabilities on a system and then help them select or even craft the necessary payload to be sent to that service in order to exploit that vulnerability. Now, the end result in most cases is for the attacker to gain privileged access on the host that is hosting that vulnerable service. So through a vulnerable web server, for example, an attacker would be able to execute his or her own commands on the actual server machine that is hosting that web server, which gives them a foothold inside of your company, which of course makes it so much easier then for them to pivot and to extend their reach and, grab some sensitive information or corrupt some important data. So a couple of these exploitation frameworks, and the most well-known one is Metasploit. Remember this one, especially for the exam. Another one is Sniper, which, just like Metasploit, is actually designed for penetration testing. It's not just a tool for bad guys, right? We're using it as a penetration testing tool to see how vulnerable we are to some detected and well-known vulnerabilities that we found in our network. And we have a couple more here that are worth mentioning, like browser exploit, which is a way to target vulnerabilities in embedded systems, or Beef, the browser exploitation framework, which attempts to target vulnerabilities in web browsers through compromised websites and web pages. There's also the ZAP, the Z attack proxy, which is a tool that helps you perform tests on web applications. And well, those tests on the wrong hands become attacks, hence the name Z attack proxy. And finally, there's PACU. That's a tool dedicated for performing a security assessment, not on your own network, but on a cloud infrastructure that you might have purchased from vendors like Amazon, Google, Oracle, Microsoft, and so on. Careful with this one. Any type of security assessment tool is going to look like, it's going to walk like, it's going to quack like an attack in the eyes of an intrusion detection or intrusion prevention system. And you can be sure that all the major cloud vendors out there have thorough security measures in place that are going to detect any type of attempts that look like a penetration test or like an attack from the outside. So don't forget to ask for permission. There are forms that are specific maintenance windows that you can reserve with that specific cloud provider, during which you are allowed, and only during that period, you are allowed to perform these security assessments. Because you're basically penetration testing, you're attacking their own infrastructure, which is a bad thing to do if you don't have proper authorization. All right, so we covered a lot of tools during the session. Don't just glance over them. Try to install them, try to run them. Install a distribution such as Kali Linux or Parrot Security. They're all free to use, so you can install them on your own machine or your own laptop and play with them. Have a look over the man pages. Have a look over how they behave. Try to scan your own home network. Don't scan anybody else, all right? And get a feeling of how these tools actually work in the real life. All right, so thank you for watching. See you next time. If you enjoyed this, leave a comment. If you want to discuss more about the topics that we've covered right here, use the comment section, like and subscribe, and see you next time. Bye bye.